Okay, so we're starting in Chapter 7, and Chapter 7 is about what we call sampling distributions. So the sort of larger context for what we're doing is we're interested in knowing something about a population. It might be we're interested in the mean of a population. We might be interested in the proportion of a population that favors or does a certain thing. But in both cases, the population is usually too large for us to actually collect data from the entire population. Right? It's too expensive, it's not feasible to do that. So in both cases, we sort of have to settle for just collecting a subset of the population that we call the sample, and then finding either the mean or the proportion of the sample so that we can learn about the population. All right, so we've discussed that sort of general idea before. What's new here is we're going to need to start getting an idea for how good our estimates from the sample are for our population parameters. So specifically, if we're talking about trying to estimate a population mean, and we do it with a sample mean, we would like to have some idea for how good that estimate is. And we sort of might have some intuition that the larger the sample, the better the estimate should be, right? And we're going to sort of make that a little bit more precise today. So once again, the context is we want to learn about a population. It's too hard to directly measure everything in the population. So we're sort of stuck with contenting ourselves with a subset of the population from which we actually get data, that's the sample, and then we calculate an estimate for the thing we want to know based on the sample. Now, if we're talking about a sample mean, x bar, to approximate a population mean, mu, then the way we're going to approach this is to think about what would happen if we took lots and lots and lots of samples of the same size. So we're going to say we're going to do a sample of size 100. We would take one sample of size 100, calculate the sample mean, take another sample of size 100, calculate potentially a different sample mean, and then think about what the distribution of all possible sample means must look like. If we know that distribution, we'll know how variable our estimates are, and we'll know how close we should expect our estimates to be to the real parameter. Now, our first big result, sort of big theoretical result, is what's called the central limit theorem, and that's a theorem that tells us what the distribution of all possible sample means has to look like. All right, so I've got a brief version of the central limit theorem here on the board. All right, so basically this says that if we take simple random samples of size n, that's here, and we do that over and over and over again, and every time we take a sample, we calculate a new x bar, and then we look at how those x bars are all distributed. The central limit theorem says that it's always approximately normal with a mean that equals the population mean, right? So the average x bar always has the same mean as the population. And then the standard deviation of the x bar is the population standard deviation divided by the square root of the sample size. Now, one thing that tells us is that if we take larger and larger samples, right, the n grows, so the square root of n grows also, which means sigma divided by the square root of n gets smaller, and so this is telling us that the larger the sample, the less variable our results. All right, if we take a sample of size 1,000, we get a lot less variation in possible x bars than we would if we took samples of size 3. Right? Those could vary a lot. Samples of size 1,000 won't. All right, so we're going to take a lot of advantage of this theorem and that fact about the variation for the rest of the course. All right, well, we're going to start doing that with just a couple of examples today. So in the first example, we have a collection, or we have a population of shelter dogs. I'm going to adjust this for a second. And we're told that the population of shelter dogs has a mean weight of 30 pounds and a standard deviation of 12 pounds. And we are going to take a sample of size 36 and then ask some questions about what we know about the average weight in that sample. So we have 36 dogs, we weigh them, take the average weight, and what can we say about that weight? All right, so we're going to apply the central limit theorem. That part's going to be new. And then we're going to do some calculations involving normal distributions, and that part is not new. We just finished an exam where part of the exam was doing calculations for normal distributions. Right, so that's going to continue. Okay, so the first thing to check when you're going to apply the central limit theorem is that it's legitimate to do so. So the central limit theorem says that it doesn't matter what the distribution of the population is. Notice I didn't say that it was normal. I just gave you a mean and standard deviation. So the central limit theorem doesn't care what the population's distribution is. It says that the X bar distribution is still going to be normal. But we have to be a little bit careful. If the population's distribution is really non-normal, so like really, really skewed or bimodal or something that keeps it from being normal, then you have to make sure you take enough in your sample. And it's a pretty relaxed requirement. We have to check to see if n is bigger than or equal to 30. And since n is 36 in this case, then yes, the theorem applies. So as long as n is bigger than 30, the central limit theorem is okay to use really regardless of how non-normal the distribution of the population is. And then the one thing I don't think I specified in the notes is that if the distribution of the population is normal, then the central limit theorem is an exact result. In other words, if the population is normal, X bar is exactly normal. If the population is not normal, X bar is approximately normal as long as you take enough in your sample, as long as n is bigger than 30. Okay, so we've checked, the theorem applies, and now we need to describe the distribution of X bar, and that's just a matter of applying the theorem. So the central limit theorem says X bar is approximately, at least approximately normal, with mean equal to the population mean, so that mean is 30, and standard deviation equal to 12, the population standard deviation divided by the square root of the sample size. So I've got 12 over root 36, and of course this is rigged to be an easy by hand example. So 12 divided by 6 is 2. And so the news that the central limit theorem reports is that the distribution of all possible sample means is normal with mean equal to the populations, but a much lower standard deviation, right? So we're taking an average out of 36 dogs. That's not going to vary as much as if we just pulled a single dog out of the shelter and measured. All right, now we want to be in the habit of kind of sketching out what this means. So our normal distribution is this bell shape, and we mark off the mean, that's the center of 30, and then standard deviations above and below 32, 34, 36 pounds, 28, 26, and 24 pounds, so plus or minus 2 pounds in each direction. So this represents the distribution of all possible sample means for dog weights when you have at least 36 dogs in your sample. All right, our first computational question is to find the probability that the average weight of those 36 dogs is between 28 and 32. 32 pounds. Well, between 28 and 32 pounds, that's one of the special places for the empirical rule. That's 68% of my observations, or 0.68 as a probability. So this is using the empirical rule. We could also use the normal calculator on StatCrunch. All right, then we have a final question for this example, the probability that x bar is less than 34. Do a different color for this one. So here I've got 34, and I want all the area to the left of 34. So again, we can use the empirical rule. Between 26 and 34 is 95% of the area. So that misses 5%, equally split on the two sides. So I would have 2.5% to the right of 34, which means 97.5% to the left of 34. I think I said 90. So to the left of 34, this probability is 0.975, again by the empirical rule. So I just want to highlight, I split this up into two pieces. Numbers 1 and 2. All right, this is new stuff, and it can be a little difficult conceptually at first because you've got a lot to kind of keep track of. We're taking one sample, but we're envisioning what would happen if we took a whole bunch of samples of the same size. We're applying this theorem, and it tells me that the sample mean has to be normally distributed, same mean as the population, but with smaller standard deviation. So that's the sort of new part, and it's challenging, so we need to take our time sort of wading through it. But I did want to point out that the second piece, where you actually start doing calculations based on the theorem, this is old, right? So we just did this, we did it on the first exam using the empirical rule a little bit, and we changed our language and notation a little bit and did it on the second exam. So this is using the empirical rule. You're just dealing with normal distributions like we were before. Right? The difference, the thing that's new, is that the normal distribution comes from this theorem that you have to apply on your own. Okay, so let me move on to another instance of using the central limit theorem, although this time it's for a population proportion. All right, so this is the example where we've got 72% of all dogs at the shelter have been microchipped already. And we're going to take a simple random sample of size 100. And we're interested in knowing the sample proportion of microchipped dogs. All right, so we're going to take 100 dogs out of the shelter at random and see which ones have been microchipped. Okay, now for sample proportions, we have a little bit more to check to make sure that the theorem applies. Let me move this a little again. So one thing we have to check is that n times p is at least 15. My n is 100, my p is 72. 0.72, sorry, but the product is 72. That's bigger than 15, so that checks out. And the second thing I have to check is that n times 1 minus p, the thing not happening, is also bigger than 15. So that's 100 times 0.28, and that's equal to 28, which is larger than 15. So my n is large enough that it works on both counts. And so I am free to apply the central limit theorem version for sample proportions. Okay. So let's see, let's describe the distribution. Now that we know that the central limit theorem applies, we know that p hat is normally distributed with mean equal to the population proportion, 0.72, and standard deviation equal to the square root of population proportion times 1 minus the population proportion over 100. Right, I think in the notes I split the square root into square root of the top over square root of the bottom. That's equivalent. Okay, so I haven't actually changed the formula. Let me go ahead and complete this. So this is normal with mean 0.72. If you get out your calculator and calculate the square root here, let's see, so I do 0.72 times 0.28 all divided by 100, and then I take the square root of that thing. I get 0.045 about. And so my distribution is a bell curve where the population mean, or population proportion, is the center, and then we would step off 0.72 minus 0.045 and plus 0.045. So if I did 0.72 minus 0.045, I get about 0.675, and then I can mark off the other points as well. And that would put me in a position to use the empirical rule for these results as well. Although I think for the question we're asked about here, the empirical rule doesn't exactly apply because I've got 0.67 and not 0.675. But just like in the previous case, right, what I've done in numbers 1 and 2 is new. Right? So I've applied the central limit theorem to get the distribution of a sample proportion, which has to be normal, same mean as the population proportion and standard deviation calculated as we just did. And that allows me to use either the empirical rule or, in this case, stat crunch to do the actual calculation. And that's something that we've done before. So here I would get out stat crunch. Right, I would have my little window where I want probability less than or equal to 0.67. The mean 0.72, standard deviation 0.045. And let's see, I just did that, and it comes out to be 0.132. So this is 0.132 would be the probability that the proportion of microchipped dogs in my sample of size 100 turned out to be less than 0.67, or about 2/3. Right, so a pretty low chance that something that small would occur. All right, now the problems on the worksheet are going to be really similar to the examples that we've just done. Just take your time and walk through the central limit theorem step by step. So the first thing you should do, even if it's not part of the problem itself, is to check that the theorem applies. Then write down what the theorem says about the distribution. Right? So before you even look at what the problem's asking, you should be writing these down. Right? Get the distribution. Once you have the distribution, the rest of the calculations go just like they did for the last exam. All right, so hope this helps. It's different. Can be kind of a lot to keep track of in your head, because sampling distributions of sample means, right, there's sort of a lot going on there. But again, hopefully this helps get you started, and we'll talk more in class.